Okay, these are the notes for pre-calculus, third hour, and it's the start of lesson 7.2, two variable linear systems. And so we are just gonna start with these notes. If for some reason we didn't finish 7.1, I think it's pretty self-explanatory, but I will address that on Wednesday as well. And so this is, feel free to pause this whenever you need to, but this is two variable linear systems. And we're pretty familiar with the things that are here as well, but I will just go over them a little more thoroughly because when we move into the next section, which is multivariable linear systems, we want to be just really firm in our process here. So even if some of the problems seem pretty straightforward, make sure that you are going through the steps as we go. And again, if you need to pause it, go ahead. So then on this slide, these are just our objectives. Use the method of elimination to solve systems of linear equations in two variables. Much more direct than graphing if it doesn't hit a grid point. Substitution can get messy, so this is kind of usually people's go-to method. And then, so use the method of elimination to solve systems of linear equations in two variables. Interpret graphically the numbers of solutions of systems of linear equations in two variables, and use systems of linear equations in two variables to model and solve real life problems. So that middle one, that's when we're going to find, that the lines might be parallel and there's no solution. The lines may coincide, and so there's an infinite number of solutions, but that doesn't mean everything will work, or they just intersect as lines and give one solution. So first we're going to go through the method of elimination. And so this, you've studied this before. Here's just a very simple situation that's showing that method of elimination to begin with. If we have these two equations, equation 1 and equation 2, when we just simply add those two equations together, we're going to find that the x variable drops out, and we'll just kind of briefly solve that the rest of the way. So when we get 3y equals 6, we'll divide by 3, and then y equals 2. And then our general way to find the other variable is just to back substitute it into either one of those. I'll pick 3x plus 5y equals 7. Put in the 2 for y, so 3x plus 5 times 2 equals 7. 3x plus 10 is 7. Subtract 10. 3x equals -3, divide by 3, x equals -1. And so we get that ordered pair -1, 2. And then, of course, we would want to check back in and just make sure that those work as we go. So this was very straightforward because right away these were going to subtract. If you remember, if they're not going to subtract, or suppose we wanted in this one to subtract the y's, we could multiply that first one by 2. That would give us their -10y. We could multiply this one by 5, and that would give us -10y, and then the y's would drop out. And so when we look at our next slide, it'll go through that process of elimination. I'll read through it with you, and then if you want to write more than the time that I go through it, you can pause this recording and kind of do that. So the method of elimination, to use the method of elimination to solve a system of two linear equations in x and y, perform the following steps. Step 1 is obtain coefficients for x or y that differ only in sign by multiplying all terms of one or both equations by a suitably chosen constant. So I think in that last one, it was 2's and 5's. And then we add the two equations to eliminate one of the variables. We solve that equation that is obtained by doing that, and then we back substitute that one answer that we got into either of the two original equations. And then we do just want to check to see that it solves both of those equations as we go. So again, we'll start pretty straightforward in these problems. If you need more time with that, just pause this recording and you can see that, or it is also in the book as you go. So here's example 1. Solve the system of linear equations. And again, it's a pretty straightforward one. The y's are going to drop out, so we'll just work through it. 3x plus 2y equals 4. 5x minus 2y equals 12. When we simply add those two, the y's will drop out. We get 8x equals 16. Dividing x by 8, x equals 2. And then putting that back in, I'll just put it in the first equation. 3 times 2 plus 2y equals 4. 6 plus 2y equals 4. And then subtract 6, 2y is negative 2, divide by 2, y is negative 1. So that gives us a solution, oops, let me go all the way back up there, of 2, negative 1. I'll just really quick check that. So 3 times 2 plus 2 times negative 1. 6 minus 2 is 4, and that's what I want it to be. 5 times 2 minus 2 times negative 1. 10 plus 2 is 12, and that's what I want it to be, so that one checks also. So that one is just very straightforward. Example 2 is just a little bit more work for us, and solve this system of linear equations. And for some reason, I just like to always rewrite the problem. So 2x minus 4y equals negative 7. 5x plus y equals negative 1. If I were here, I would ask you which equation or which variable you want to eliminate first, but I'm going to pick for you. And since the y's have negative 4y and positive 1, I can just multiply one of the equations. So I will multiply this second equation by 4, and then that's going to make the y's drop out. So I'll just rewrite my first equation, 2x minus 4y equals negative 7. I'll multiply through by 4, and please make sure you multiply all the terms. I guess as a student, that was always one of my challenges, just to remember to multiply everything. And to be honest, it was usually that what it's equal to that I forgot to multiply by. So I know you will not make the mistakes I probably made. 20x plus 4y equals negative 4 when I multiply, and then adding the 4y's and negative 4y will cancel out. I'll get 22x equals negative 11. I'll divide by 22, and x equals negative 1/2. So a little less desirable than sometimes. And then I'll just substitute that back in. And you know, since x is negative 1/2, there is a better equation. Since that one will make the fraction disappear, that's where I'm going to put it. That would keep the fraction. So I'm probably not going to use that one. And so I'll take 2 times negative 1/2 minus 4y equals negative 7. That will be 1 minus 4y, or excuse me, negative 1 minus 4y equals negative 7. I'll add 1, negative 4y equals negative 6. Y equals 6/4, which will be 3/2. So my solution for this one is negative 1/2, comma, 3/2. I'll do a quick check. And generally, I just want to make sure that these are going to work. So I'm going to just go from the one I can see there. So 2 times negative 1/2 minus 4 times 3/2. This will be 1 minus negative 1 minus 6, which is negative 7. So that one worked out. The other one, 5 times negative 1/2 plus 3/2. And so this is negative 5/2 plus 3/2, negative 2/2, or negative 1. So that one checked as well, just to kind of make sure that I know things are happening there as as I want to. Um, if you're understanding that pretty well, I could skip this next one, and the next two are pretty similar. Let me just kind of go to this number 3 here. Um, Oh, things that you can do with systems of equations. You can interchange any two equations, and you might be thinking at this point, well, why would I want to do that? But as we move on later to the multivariable linear systems, that'll be an important thing. Multiply an equation by a non-zero constant, and then adding a multiple of one equation to another equation in the system. So just some things to keep in mind as we go through. Now, this one is solving a system of linear equations. You know, maybe because I'm not here, I will kind of go through this one as well. So this one is 5x plus 3y equals 9. 2x minus 4y equals 14. So I'm going to make the y's drop out in this one because they have opposite signs. So I'm going to multiply my first one by 4, my second one by 3, and then my new equations will be 20x plus 12y equals 36. 6x minus 12y equals 42. When I combine those, I'll get 26x equals 78. Dividing by 26, I get x equals 3. And then finding that other variable, I'm going to put it in just my first one. 5 times 3 plus 3y equals 9. 15 plus 3y is 9. I'll subtract 15. 3y is negative 6. I'll divide by 3. Y is negative 2. My solution here is 3, negative 2. And I'll do a super quick check. 5 times 3 plus 3 times negative 2. 15 minus 6, that is going to be 9. 2 times 3 minus 4 times negative 2. 6 plus 8, that is going to be 14. And so I'm good to go. So just kind of a little refresher of that elimination method. Our next problem, is this number 4. And the reason I want to go over that one is just because it is a little unique in that it has a lot of decimals and things like that. So for number 4, and I will write the problem here. 0.02x minus 0.05y equals negative 0.38. 0.03x plus 0.04y equals 1.04. And so when I have one like this, my hint to myself and to you is if I multiply, before I even multiply to get rid of a variable x or y, I'm actually just going to multiply it to get rid of all these decimals just because they're a little more of a hassle to work with. So my hint is to multiply both equations by 100 in this case, or if they're fractions and I wanted to get rid of the fractions, whatever the denominator or the common denominator would be, to get rid of decimals. And so what that does for me is that gives me 2x minus 5y equals negative 38, and 3x plus 4y equals 104. And so to me, that just looks more pleasant. And I'm always happy if a problem looks a little pleasant. This one I decided just to get rid of the x because I haven't in the last one, even though the y's have opposite signs. So I'm going to multiply the first equation now by 3, the second equation by negative 2. And when I do that, I'm going to get 6x minus 15y equals negative 114. Negative 6x minus 8y equals negative 208. Combining or adding those two equations, I get negative 23y equals negative 322. And then when I divide by negative 23, I get y equals 14 on that one. Then my next step is just to find x. I'm not going to even think about putting it in those decimal ones just because it would be a little more challenging. And I'm just going to put it in that first one again. Whatever you choose is fine. I'm going to draw a line there. So 2x minus 5 times 14 equals negative 38. 2x and 5 times 14 minus 70 equals negative 38. I'll add 70. 2x is 32, and divide by 2, x equals 16. And so in this one, my solution, and I'll write it above here, is 16, 14. I don't have a calculator at the board, so for this one though, I would just to, buffer myself in case I made a mistake along the way, from there. Personally, I would use a calculator and just 0.02 times 16 minus 0.05 times 14, enter, see if it's negative 0.38, and then 0.03 times 16 plus 0.04 times 14 to make sure that's 1.04. And I'll leave that to you if you'd like to pause this and do that. And so then if we were in class together, I would have you answer some questions here. And I would ask you to do this. It says, know both the substitution and elimination methods. On paper, write the following and turn it in. Write your answers to 1 and 2 in complete sentences. So I might ask you this when I get back. What are the differences between the two methods of substitution and elimination? What are the advantages of each method? Kind of processing in our brains to, like Professor Ouija said to us one day, if you don't use the neurons in your brain, they go dormant. So to keep that from happening a little bit. And then number 3, I'd like to go over with you. It might be looking, it's very general, and so I would like to just go over how to do this problem, and I would have asked you to give it a try, but I think we'll just kind of do this together a little bit as a good exercise. And now I'm kind of second thinking that, maybe I will ask if you'd like to try it. You could turn that in to me tomorrow, and maybe I'll go over that tomorrow when we're all actually here together. So let's take a minute then and just move on to the next thing. The graphical interpretation of solutions. So for this one, it's just really a matter of using that graph to kind of help us decide the situation that we have for the number of solutions. So it's possible for a general system of equations to have exactly one solution where the lines intersect, 2 or more solutions where they are the same line, essentially multiples of each other, and also having no solution is the other situation. So just make sure that you're aware of this. You might want to write something down. You've encountered this before, the graphical interpretation of solutions, and I am going to give you a little extra information there on this slide. It'll be on the next slide. So for a system of 2 linear equations and 2 variables, the number of solutions is one of the following. And so number 1, if there is exactly one solution, the 2 lines intersect at one point, the slopes of the 2 lines are not equal, and these are called consistent and independent. Consistent and independent. So then the next one is and consistent means it has at least one solution. And I'll just maybe write that below there. At least one solution. And then number 2 says it has infinitely, I just wanted to put an arrow to consistent, sorry. Infinitely many solutions. The two lines coincide, are identical if you graph it, and the slopes of the two lines are equal. These are also considered consistent because they have at least one solution, but then we'll say and dependent. Because they are essentially the same line and they have an infinite number of solutions, they are considered dependent. And then step 3. Case 3 is that there's no solution, so the two lines are parallel. And if that happens, then the slopes of the two lines are equal, and that is called inconsistent. Inconsistent. So inconsistent, no solution. No solution is what it means to be inconsistent. So to me, that makes great sense. Inconsistent doesn't work. Consistent works. Independent, one solution. Dependent, multiple solutions. You know, they're kind of the same line. Inconsistent is going to be that parallel. And so when we encounter these second and third cases, that's going to be when the variable drops out when we're eliminating, both variables, excuse me, drop out when we're eliminating things. And then when that happens, in one situation, they will be the same thing. In one situation, they will be parallel. And if they're parallel, you get a false statement. And if they're the same line, you'll get something that is equal as we go. So that is that. And this just talks about the consistent and inconsistent. So then let's look at these little 3 situations. And I don't have a lot of space here, but I kind of want to go over solving some of these. So they notice that first equation in each one is the same. These are all the same equation. And then, you know, these either are kind of similar to each other or a little bit different. So that's what we're anticipating, that we'll get one solution, no solution, or an infinite number of solutions. So for this first one, notice this. If I multiply everything here by 2, and I'll just do that right kind of above here, I'll get 4x minus 6y equals 6. And if I add that to the bottom one, 4x minus 4x is 0. Negative 6y plus 6y is 0. And so that whole side is equal to 0. But then 6 plus 6 is 12. And that's a false statement. And so that is going to be no solution. And so that's going to be the parallel lines. So for A, it's I, the parallel lines. And it is inconsistent. Inconsistent. Just to kind of let you know that. So if both variables drop out and it's something that's false, the lines are parallel and there is no solution to that. So the next one I'll just use a different color for. And for this one, if I look at this and I want to make a variable drop out, I think I'm actually going to multiply this second one by -2. And I'm going to write it kind of right below here. I'll get negative 4x plus 12y. Or excuse me, I am not doing that correctly. My apologies on that. I was, I think, looking at the wrong thing. Whoops. There we go. So when I multiply that second equation by -2, I was multiplying the first one. I'll get negative 2x minus 4y equals negative 10. When I add that first to the third, I'll get, and I just don't have a lot of room, negative 7y equals negative, I must have done something wrong here. negative 2x minus 4y and equals negative 10. So I get 0 for the x's, minus 7, negative 7y equals, oh, negative 10 plus 3 is negative 7, and then y equals 1. When y equals 1, I'll substitute that back in. X, I'm going to use the second one, plus 2 equals 5, so x equals 3. So it has one answer, which is 3, 1, and that's the point of intersection. So this one is I. And these are consistent and independent. So we probably know what the last one is, but let's just validate that and kind of see what happens. So on this one, I'm going to multiply the first equation by 2. When I do that, I get 4x minus 6y equals 6. When I add that blue one above and the bottom one there, I get 4x minus 4x is 0, negative 6y plus 6y is 0, but then I also get 6 minus 6, which is 0. And this is a true statement. When it's a true statement, I just want to kind of maybe go a little further than you have maybe before. First of all, it's I. They are the same line, and so they are consistent and dependent. Dependent. But in this case, we can actually give a solution, and maybe you have or haven't done that in the past. So I'm going to extend this a little bit. I can take either of those equations. I'll take the first one, 2x minus 3y equals 3. I'm going to solve it for y, and when I do that, I'll get subtract 2x, so negative 3y equals 3 minus 2x, and then divide by negative 3. So y equals 3 minus 2x divided by negative 3. I'm thinking of Ellie saying, oh, I would have just moved it the other way, which was a good idea. So I'll multiply each side by, or the top and the bottom by negative 1. I'll get 2x plus, or minus 3. 2x minus 3 over 3. And then I can write my answer in a very general way as an ordered pair. So my solution here would be x comma 2x minus 3 over 3. And sometimes the book authors will write that as like a comma, and then 2/3 a, in this case minus 1, kind of putting that together. Either answer would be fine with me as you go through this. Then the next problem is solve the system of, oh, that's this one we just went through, and that just kind of goes through that one. So the next one says solve this system of linear equations. And so one of these situations might happen to us, and I'll just kind of do this one with you as well. And so x minus 2y equals 3, negative 2x plus 4y equals 1. And I'm going to multiply this top one by 2. I didn't leave myself a huge amount of room, so I'm going to fix that a little bit. I'll write my problem number up here. And I'm going to multiply now that first one by 2. That'll give me 2x minus 4y equals 6. The bottom equation, negative 2x plus 4y equals 1. When I add these together, these cancel out, those cancel out, I get 0 equals 7. That is false. So that is really not the answer. It just helps you get the answer. The answer is no solution. No solution. And if asked, it's inconsistent. And also if asked, these are parallel lines. Okay? So that's kind of what's happening in that problem. Then our next one is, is solve this system of linear equations for number 7. And again, I'll write it 2x minus y equals 1, 4x minus 2y equals 2. And for this one, I'm going to multiply the top equation by -2, and I'll leave the bottom one. So I'll get negative 4x plus 2y equals -2. 4x minus 2y equals 2. When I do this one, these cancel, so I get 0 equals -2 plus 2 is 0. So this is true. And again, true isn't really the answer to this, but here are the things we can give. So to give the solution, so this is, I don't know if you've done it this way before, and to find the solution, I pick one of my original equations. So 2x minus y equals 1. And I'll use Ellie's system. I'll subtract y and subtract 1. So 2x minus 1 equals y. And so then that means my ordered pair can be x comma 2x minus 1. And so now my solution will be very general, a comma 2a minus 1. And then really I'll write where a is an element of the real numbers. So that's my solution for that one. If asked, these are consistent because there's an answer, at least one answer. They are dependent because there's an infinite number of solutions, and the lines coincide. And they're the same line as we look at that. Now, the next problem is an application problem, and I do want to do that one with you, so I'll maybe have you, you know what, I think what I'm going to do then is I'm going to go back to this slide. I'm going to have the teacher give you a handout of this, and then have you fill that out and turn it into the tray, and then you can use your time to work on homework and things like that. So have a good rest of your day, and I will see you tomorrow.